All right, let's have a look here. Number 52. Is that the water running into a base problem? Oh. What number? Yeah. Oh, never mind. This is the one that gives you, I remember. This is one where you're trying to find the values of A, B, C, and D?
Yeah.
Yeah, okay. Okay, so let's do, I'm gonna do 51, which is very similar.
Yeah, it's just the next one.
It's the next one.
What's the answer number 2?
Would be
It's like, I don't know why. What is it? I think I was reading. That's something that they It's Alexis. Yeah. It's, yeah, no.
Okay, so here's the goal on this one then. We want to find the values of all the coefficients in this polynomial if we know that this is true. We know 3 things for 51. We know that there is a relative max at the point 3, 3.
52?
What's that?
52, not 51.
I thought I'd do 51, which is just like 52. And you guys can do, I mean, the steps are almost the same.
No, because you don't.
Okay, suggestions. This is a really good problem, actually, I think. Some suggestions here. If we want to find the values of A, B, C, and D, those are 4 unknowns, right? So let's talk about this just algebraically. If we want to find the values of 4 unknowns, how many unique equations are required to do that? Why don't everybody close your Chromebooks up and take a look at this. This is one you'll probably, there will be some built-in review here, I would think. Right, we need 4 equations, right? We need 4 equations to find the values of 4 unknowns. Preferably, we'd like linear equations if we could. Well, we're going to be able to get that because, I mean, how am I going to get an equation? Somebody give me an example of just the fact that we have a relative max at this point. Let's forget even the relative max part. If we know the function goes through this point, how can we turn that into an equation involving A, B, C, and D? What's this mean? What's an ordered pair mean? That's a value of x and y. Okay, so when x is 3, y is 3, right? So how could I turn that point into an equation involving the unknowns A, B, C, and D then?
Just plug it into the original equation.
Yeah, I could just plug it into the original function, right? And so this point right here, I'll try to kind of color code this here. So that point right there gives us the equation, for example, A times 3 cubed, which is what? 27, okay. So 27A plus B times 3 squared. Everybody see this? plus c times x, which is 3, so 3c plus d equals f of x. What's the value of f of x when x is 3? 3. So there's an equation, right, involving a, b, c, and d. So what's my strategy then for this, you think? For a problem like this? Say it again, Lois? Yeah, I want to come up with at least 4 equations, right? Now, these are pretty big, ugly equations, though. I mean, these are, if I just use the points, I'm plugging them into the function, and I'm getting back equations that involve A, B, C, and D. But I could also do something else kind of tricky here. I could do something like this. If I know that I have a relative max at 3, 3, a relative max might be helpful to us. It's been a while. It's been a couple weeks. So what's interesting to us in terms of calculus about a relative maximum? The derivative is 0 there, right? So we could take our function up here and we could say, okay, well, we got our function. Let's calculate the derivatives also, right? So what is the derivative of f of x? Yeah.
Did you put in the A or the B for
I didn't. I put in x. What I did to get here is I just said this. I just said that f of 3 equals 3. So I plugged in 3 for x, all the x's, and I plugged in this whole thing is a 3. See what I'm saying?
So the first thing.
Right. I mean, this ordered pair means if I input an x value of 3, I get back 3, right? So all this is really saying right here is that f of 3 equals 3, right? So I'm actually plugging in what I did here. Now, let me do something here. It might be helpful. Yeah. Let me do this. Oh, shoot, anyway. Man, is it just hotter than hot here? Just me.
Smells good.
That's hot.
If I fall asleep up here, if I nod off up here, somebody wake me up. Right. Okay, to get here, whoops. Let's just real quick, I just want to demonstrate, just so this is abundantly clear, how did we get this answer? All we did was we said a times 3 cubed plus b times 3 squared plus c times 3 plus d equals 3, right? When I plug in 3 for x, I get back 3 for y, okay? So the idea now, though, is let's take advantage of the fact that we're given some information here about where we have a relative max and a relative min. How could that be useful? Well, if I take the derivative, what is my derivative again? You guys started to tell me.
3x squared plus bx.
What's the next term going to be? Say it again.
2b.
2bx, okay, good, plus c, and then the d goes away, right? So there's my derivative function. But I know from this statement right here that that's a relative max. I know that f prime of 3, when I plug in 3, what's the result going to be? If I evaluate my derivative function at x equals 3, what's the value of the derivative?
27a.
It's a relative max.
0.
0, right? Okay, so f prime of 3 equals 3a times 3 squared plus 2b times 3 plus c, and that whole thing has to equal 0, right? So I get back another equation. Now, why is this one maybe kind of helpful? Look at this equation. 3 squared is 9 times 3 is 27. So I get 27a plus 6b plus c equals 0. That's a little simpler, right? It's only got 3 unknowns in it, right? So that might be useful to have, right? In fact, I probably want to take advantage of all 3 of these calculus statements up here because they give me equations in my system that have fewer variables to grapple with at the same time, right? So what is this one right here telling me? If I have a relative min at 5, 1, what's that saying? How could that's a first derivative issue, right? So what's the value of the first derivative at x equals 5?
0.
0. Okay, so that's giving me another equation, right? So that's telling me then, let's make this different color. So if I have a relative min at 5, 1, then that means that f prime of 5 equals 0, right? And so that's like saying f prime of 5 is, there's my f prime, right? Is just going to be 3a times 5 squared plus 2b times 5 plus c. And what does that become? So what's 3 times a times 5 squared? 75a plus 10b plus c equals 0. Okay, so I'm going to go ahead and circle these. We've got 2 equations. Our goal was just to get 3, right? So we started with that one.
Only 4.
Or say it again.
4.
Did I say 3?
Yeah.
Yeah, we need 4, don't we? Because we have 4 unknowns. So then what about the last one, the inflection point one?
The derivative of that.
Okay, so that's the second
Second
derivative, isn't it? Right? So what's our second derivative going to be? If that's our first derivative, what's our second derivative?
6ax plus 2b.
6, okay, 6ax plus 2b. That's really simple, right? And so what then is this telling me right here? If I have an inflection point at 4, 2, that's like saying f double prime of 4 is equal to what? What must happen at an inflection point?
0.
0, okay. And so if I evaluate this expression at 4, I just get 6 times a times 4 plus 2b. And so I get the equation, what is that? 24a plus 2b equals 0, right? And so now I've got a system that involves 4 unique equations in 4 unknowns. And so we ought to be able to solve this linear system. Did we have to use all of these calculus? I mean, we didn't really have to. I mean, we could have just used, we could have used each of these points and come up with 3 different yellow equations involving A, B, C, and D, and just used one of the calculus ones. But if we were going to do this problem without technology, if we're going to do this problem kind of by hand, solving this linear system, this would make it much, much easier, right? So let's look at what our linear system, if we deal with all these equations now, let's just collect them all in one place. So our equations are this guy, 27a plus 9b plus 3c plus d equals -3. Now that's written in standard form. I realize that our original equations were written in terms of the independent variable x, but what we've come up with here, really our goal is to find the values of the coefficients, right? So we've come up with 4 equations in the 4 unknowns a, b, c, and d, right? Now these are linear equations because the a's and the b's and the c's and the d's are by themselves and they're not taken to any power, right? So it's weird to think of, I mean, I know this has been a little while, but this would go back to, I mean, it'd go back to Algebra 2 a little bit, but also last year when you guys did solve. Do you remember how to solve these with a calculator using matrices? You do, is that something you guys remember? I know you guys do it in chemistry a little bit too. I'm gonna show you a good trick for this. I think we need to maybe review this a little bit. I have a feeling, I'm just getting the sense that this might be a review-worthy topic. We wanna, this is a linear equation. We're used to linear equations being lines in a plane, but they don't have to be, right? A linear equation, in a broader sense, just means that all of that it can be written in a way like this, where each term has a linear variable. So the variable is by itself multiplied by some coefficient. If I were to take, for example, something like this, just a little review here. We know that ax plus b equals c would be one way we could write this. Or mx plus b equals y, whatever you want to say. Actually, let's do it that way. Let's write it this way. We know what that is. That's just a line in a plane, in the xy plane. What is this? I could also write this, let's write it in this form. I could also write it in that form, right? You guys are used to writing it in the form with capital A's there. Ax plus by equals c, right? And that's what you called standard form, right, for a line. It's just a line in a plane. What if I did this instead? Ax plus by plus cz equals d. What's that? That's a flat plane in space. Right? So that's an infinite plane floating around in a three-dimensional space. We can generalize this. What if I did let's do plus d, we'll call it w. What's that?
3D object floating in space.
That's a 3D object embedded in a four-dimensional space. And so on and so forth. They're all linear, right? They're all linear because they all are to the first power and they all have just constant coefficients, right? So they all, I mean, those are all linear. They're just, but linear is different than, it's bigger than what you probably once thought it was. Okay, so we want to solve this linear system. Here's equation 1. We're going to write all these in standard form. So they're written in increasing order of variables, right, set equal to a constant. We'll call this equation 2, that's fine. So we get 27a plus 6b plus c equals 0. Another equation, call that equation 3.
Why did you change the first one to -3?
Did I do something bad here?
The first equation was -3.
Wasn't it? Oh, it's positive 3. Yeah, you're right. I don't know, it's a good question. Why did I do that? And then our last one's right there. So there's our 4x4 linear system. So how could we go about solving that manually?
They all add up to 3.
Say it again.
Could you do it like they all add up to 3? Here's individually each. 0, 0, 3.
I mean, yeah, I suppose you could. But if we're going to solve this, our goal is just to, we want to just gradually eliminate variables, right? So could I use one of these equations to write one variable in terms of another variable?
Set them to each other because they will equal zero.
Say it again?
You can set them equal to each other because.
Yeah, you could. You're right, you could. But if I get, what I'd really like to do when I'm trying to untangle something like this, I'd like to be able to just gradually work through and eliminate variables. And what that's called is we're going to collapse the 4x4 system into a 3x3 system. And you see stuff like this. I mean, you guys will do a ton of this stuff if you go into engineering later. I mean, like this is the kind of thing you'll do with matrices and tensors when you're doing quantum mechanics, or if you're looking at optical systems. I mean, this is really common. I'm going to show you a shortcut on a calculator in a second, but let's just talk about how we could approach this. Nick, you had a-
A equals, or 12A equals B.
There you go, good. So one thing we could do is we could take this last equation here, we could do some stuff to that, right? I could divide both sides by 2 and get 12A plus B equals 0. So then I can isolate B pretty easily, couldn't I? What's B equal to? Okay, that's a good substitution equation. Then every place I had a B, I could plug in a negative 12A. What's the purpose of that? What's that going to do to all these other equations? Eliminates a variable, right? It collapses the system down, so it's a smaller system we're dealing with. Eventually, we're going to want to know what the value of B is, but that's simple. We'll eventually just come back and plug in the value of A to find B, right? But this allows us to take this top system up here, this top part of our 4x4 system, and turn that into a 3x3, doesn't it? Right? Do you see kind of the benefit of that?
So don't we want to start with the third one? Because then you could make the top one equal to
You want to start with the fourth one because the fourth one gives us, we only have two variables.
And then after you get the fourth one, then work the third.
Right, exactly. Then we'll just work our way up. Exactly. So now we could go through and rewrite this thing. I think you see what I'm doing here. And so we're just gradually going to collapse this thing down to where eventually we'll just have a simple 2x2, right? So this would then become, if I make this substitution, 27A plus 9 times B. We don't maybe have to go through the whole thing, but let's just take it a little ways. This guy is 75A plus 10 times 12A plus C equals 0. And if we clean that up just a little bit, that becomes the 3x3 system. If I combine these, it's 27A minus 108A is what? What is that?
So what was it? 81.
Negative 81 plus 3C plus D equals 3. How about down here? We get 27A minus 72A is 45A, negative 45A. And then down here we get 75A minus 120A, so that's negative 45A. Okay, so that, so these two right here ended up being the same. So they're not, in this sense, those aren't unique. And that, later on, you're dealing with, when you take linear algebra in college, you'll look on that, this may be a little bit of a problem. You look on that as having to go back and maybe grab a different, in some situations, have to go back and grab a different equation because these don't give us two different pieces of information. But for now, we're fine. Because really for now, all we want to be able to do is go in and solve for example, C in terms of A, right? So we could say C equals 45A, right? And we could use that information to go up here and solve for, say, D in terms of A or something like that, right? You get the idea? We're gradually just collapsing this thing down. Now we've got another substitution equation. If I plug this guy back up into here, we could get negative 81A plus 3 times C, but C is just 45A. And now I could solve for, let's say, D in terms of A, right? And gradually, we're just gonna whittle this thing down to where we can get an answer for, we'll get down to one variable, and we can solve for one variable, get that value, and then just go back. Once I know what A is, for example, I can go back and find out what C is, et cetera, et cetera. I don't want to spend tons and tons of time going through, this solving a linear system, because you guys have done that a ton. But let's set this up on a calculator once, so we can see how to do this all in one fell swoop. Okay, on a calculator, there's a really slick way to do this, which I wager to say you haven't seen. You've probably done this. Where and when have you guys done solving linear systems using matrices? Chemistry, pre-calc, probably a little bit. Honors Algebra 2, you probably would have done it too, I'm guessing a little bit. Okay, and you've always probably done this using a matrix equation, right? Solving a matrix equation. You set up a matrix equation like this. The matrix equation, if I made this all into one big matrix, this would just look like the coefficient matrix 27, 9, 3, 1, right? Times the variable matrix A, B, C, D. I got to fill in all the equations equals the constant matrix 3, 0, 0, 0. Is that looking familiar? Right? Right? And you guys solve that by doing an inverse matrix of multiplying both sides by the inverse of this matrix to solve for the variable matrix. Is that how you guys have done it? Right? You would go in and you'd call this like matrix A, and you'd call this matrix B, right? Is that right? And then you would have said something like this. You would have said, if I have matrix A times matrix X, which is our variable matrix, equals matrix B, you could have multiplied each side through from the left by the inverse of A. Correct me, I'm seeing some blank, but that's how you did it, right? So you would have said A inverse times A times X equals A inverse times B, and those cancel to the identity matrix. That's how you would have done it. Yeah, I got a better way to do this. We can take this setup and we can do what's called an augmented matrix. You can do this all at once, and it's a far superior way of doing it, because you can tell when you use this method, if you get an answer that is not unique, you can't tell if the answer is no solutions or infinitely many solutions. There's no way to distinguish between the two. Okay, but if you use this method I'm going to show you now, you can. You can tell when there's no intersection, when there's no solution, or when there's an infinite number of solutions, and you can even know then what the constraints are on the variables. I mean, we're getting into some higher level stuff, but I'll show you what I mean. So let's take this matrix, and all we have to do is is write this instead of a 4x4 times a 4x1 equals a 4x1. We'll just write this in echelon, right? So we're just going to write this as 1 4x5 matrix. Where we're going to add, we're just going to combine A and B into one matrix. Okay, so there's our matrix. Now in our calculator, we'll enter that. Wow, okay, was I just doing this? Oh, I've never doing this. Okay, so let's go, I think I'd use, go to matrix, second matrix. We're gonna go, say it again. Go to second matrix and we'll go edit. Yeah, then we'll go edit. So we go over to edit matrix A, and then we're just gonna set it up like this, right? Oh, did I? Oh yeah, these are, okay, so those are separate columns. They look like, right, that's a 3 and a 1, not a 31 and a 10. So enter this one just like it looks up here. And use the enter, this is kind of just a little, just a little hint. When you enter matrices on a calculator, you want to do it like you're reading a book, right? So you're entering the first row, and that way you can enter each entry in the matrix is separated by an enter on the calculator. So 27, enter, 9, enter, 3, enter, 1, enter, 3, enter. And then it jumps me down. See what I'm saying? 27, enter, 6, enter, 1, enter, 0, enter, 0, enter. And it jumps me down. Okay, so is everybody there? Okay, now all you have to do with this, you have to quit for some reason. We're going to go back into the matrix menu. We're going to scoot over to the math menu in the matrix screen. Go up, instead of going all the way down, just hit the up arrow to go up from the bottom. We're going to go to what's called reduced row echelon form. That's B. So scoot up to B. And then we're going to call, so we're going to do reduced row echelon form for matrix A. So we go to the matrix screen and we use the names menu to grab matrix A, close the parentheses, and hit enter. Okay, and if we do that, okay, so the way we've written this, we didn't get a solution. We didn't get a solution because, and that goes back to this part. That goes back to this part right here where we ended up getting the same, because these reduced to the same equation. When we try to make our substitution, those collapse. So what we have to do, and this is always an option. We need to replace one of our first derivative equations with a different one. So let's just use the equation that comes from the 5 and the 1, right? The big equation that comes from the 5 and the 1. So let's take this guy right here, and let's replace that one with, instead, what do we get when we plug 5 into our function? Well, we're going to end up getting something like this, right? We're going to get a times 5 cubed plus b times 5 squared plus C times 5 plus D equals 1, right? So that becomes, see if we can do that all in our head, we're running out of time here. What is that gonna become? A times 5 cubed is 125, right? So we're gonna get a 125A plus B times 5 squared, 25B plus 5C plus D equals 1. Let's just take that line right there. So the coefficients are 125, 25, 5, 1, 1. And let's go over to our matrix and let's make that substitution. Let's go down and replace. Let's replace one of our, either row 2 or row 3. So we'll just go down. So this one was 125, 25, 5, 1. Wasn't it 1 equals 1?
It was
Yeah.
1.
Okay, let's try this again. So now if I quit and I go up and I'm gonna, I think I can
You can just hit enter.
just do that, can't I? Just grab that guy.
Did you go to the reduced row or something?
Okay, here's why. Look what this does.
Where
So this, say it again.
Where was it?
Oh, it's reduced row echelon form is in matrix, stream, math menu, RREF. So look what this told us here. This told us, now, this is in echelon form. So this column right here corresponds to the coefficient of A, coefficient of B, coefficient of C, coefficient of D. And then this is the constant, right? So what does this first line tell us? 1 times A equals 0.5. What does this tell us? 1 times B equals -6. 1 times C equals 22.5. And 1 times D equals -24. Tells us everything we need to know right there. Now, if you end up with, well, I'll show you this later. I mean, these are all going to work.
Wait, so what was that first one we got? Why did we go back and change it?
So the first one we got, the problem with the first one was that we ended up with 2 equations. I can show you where this came from. I wish we had just a little more time on this. These equations, if you look at these equations we got,
Order. Yeah, like which rows?
when we started to solve our equation, and we solved for B in terms of A, and we substituted into these 2 equations, the problem was when we did that, we ended up getting, on the next page, I think it was, we ended up getting, when we made our substitution, we got 2 identical equations. That's not going to work, right? Because then this system right here that needs to be a 3x3 system, it's not. It's only a 3x2 system, right? I have 3 unknowns, but only 2 unique equations. And so we can see right there that this collapsed, and we have to use a different initial equation other than one of these 2. Where did these come from? These are equations 2 and 3, which came from the derivatives, right? Those were the ones that came from the relative max and the relative min. Okay? And so those 2, we can't use those 2 together if we want to be able to solve the system. You know, honestly, you could probably predict that because, I think I'll close it there. That's a lot of review. I want to come back and maybe look at another example or 2 of that, because I feel like that's about 3 weeks of linear algebra in 40 minutes or less.
Can't
So
you
it's
just
a
tell
lot.
right there that they have the same, I don't know, form, they're both equal to 0, and so they're like.
Right here and right here.
Yeah.
Yeah, the fact that they're both equal to 0, I think you can see that's going to cause problems. If I solve for C 27, 10, it's going to be, you know, that probably, I can't answer that. That probably is gonna,
At least into.
yeah, if I had been, you know, I think when you're doing more linear algebra, you kind of get more of a feel for that. And I just haven't done it in so long, I can't really remember why that would be the case, but I think you're actually on something there. Have you guys ever seen that reduced row echelon form trick
Yeah,
before?
we did that last year. We didn't do that first one you showed us.
But you did do the reduced row echelon form? Okay, good.
Oh. Really?
Did Mr. Cooper show you the reduced row echelon form?
Yeah.
Okay, good, good.
That really nice. I did my mom about it too. Yeah.
So that's, Cooper showed you, that's good, that's,
Yeah.
I showed that to him a couple of years ago, and I know he used to do it the other way, and this way is way superior.
You did? I don't remember that at all. I remember John. Yeah, I remember Florian fixed it actually. I remember it fixed it most.
Shelley showed you, you guys went through that in biology, solving linear systems in there too?
That's it, fix it.
Yeah,
Oh, I meant Biddle.
Bidorf, oh, okay.
I remember Biddle as well, yeah.